Welcome to this class. In the last session, we have briefly gone through the sample preparation method by FIB. This is a focused ion beam microscopy method where we used the focused ions. So usually we will use gallium ions, and these gallium ions usually at room temperature these exist as a liquid, right? Because their melting point is around 29.8 degrees Celsius. So we have briefly gone through the ion column. We started with the gun source, as I have told that time that the gun source, in the gun source you have a usually a tungsten needle, okay, a sharp tungsten needle, and there is a reservoir, okay, and this is a gallium reservoir, and when uh, this gallium reservoir, usually from there the liquid gallium flows to the tungsten tip and it forms a Taylor cone, okay, and usually the electric field, so you will have a extractor plates, correct, and these electric field pulls the gallium ions. Extracted plates have negative potential, you will keep the positive potential, so your gallium ions gets pulled from the this Taylor cone, okay. So and there is also a opposite force. This is due to the liquid tension, surface tension in the liquid gallium, and that acts as a against as a electrostatic force, against electrostatic force, and when they balance together, then there will be a formation of a Taylor cone, which is around 2 to 10 nanometers or 5 nanometers with a tip radius, okay. So these, then the electrons from the gallium gets tunneled through the tungsten tip, okay, and this involves the field ionization of the gallium to the gallium plus ions. This is called field ionization. Then due to the electric field near to the tungsten tip or in front of the Taylor cone, there will be a field evaporation, okay. These are accelerated towards the column. So this is your FIB column, correct. These are the extractor plates, right. So now what we'll do is we'll also so this is particular the what we call it as a gallium liquid metal ion source, okay. Usually we'll call as a liquid metal ion source for the ion emission, okay. So now what we do is we will briefly describe the ion optics. What are the role of different components in the ion optics in the ion column, okay. So as we had drawn in the last class also, okay, this is your cross section, fine. So you will have a ion source, then you will have a condenser aperture, then you will have a condenser lens. This is called condenser lens, sorry, this is not aperture. Then you will have a aperture which is having a different size holes, okay, to pass the beam, fine. Then you will have a quadrupole, you have a quadrupole lens. This is called quadrupole lens, okay. Then you will have a blanking plates, these are called blanking plates, and then you will have a octopole, you will have octopole, correct? This is called octopole. And then finally you will have a objective lens. This is called objective lens. Okay, so the ions are get accelerated towards down of the column. Okay, these are the flight path of the ions. Okay, so these are the ions which accelerated towards the through the difference in potential. Okay, if you zoom this position, this part, then you will have a source with these extractor plates. Okay, due to the potential difference, these gallium plus ions gets accelerated down the column. Okay, this is your column. Now this particular ion beam will then go through a series of lens systems and apertures like condenser, objective, then apertures, correct, before it reaches to a specimen. Before it reaches to a specimen. Okay, so what is the use of condenser? So as its name suggests, this condenses the electron ion beam, correct, and this forms the beam which is then scanned across the sample surface, by the octopole. Okay, these are referred to as scan coils. So by using these scan coils, the ion beam gets deflected and can be scanned on the sample surface. Okay, the function of objective lens is to focus the ion beam, okay, on the sample. Okay, and the astigmatism is corrected by the coils which are present in the octopole. Okay, so what is the function of quadrupole lenses? Quadrupole functions is this uses for the mid column steering of the beam during alignment. Okay, so your quadrupole lenses and the octopole lenses, they are used to for the steering of the beam during the alignment or the sample surface on the movement of the beam on the sample surface. Okay, so one difference between the lens system in a normal electron microscope like in SCM or TM and here is in normal electron microscopes usually you use the electromagnetic lenses. Okay, so they will generate the magnetic field. Okay, so but here you use the electrostatic lenses. Electrostatic lenses for the ion column. Okay, so there is a reason for that, correct? So in SCM and TM you use the electromagnetic lenses. In SCM or any electron microscope. Okay, this difference is due to the difference in the source. So in electron microscopes you use electrons for your imaging or for the interaction of your electrons on the sample surface. Okay, in SCM or TM. But in the case of ion microscope or ion beam microscope, you use ions, for example gallium plus ions. Okay, now and in electron microscopes you use electromagnetic lenses, but in ion beam you use electrostatic lenses. Okay, so why this is different? So in electromagnetic lenses, correct, usually the force which is exerted by the magnetic lens on a charged particle or we can tell as electron on a charged particle in the case of electromagnetic lens, it is directly proportional to the velocity. Okay, and in the case of ions, so in electrons here it travels very fast, their velocity is very high, and the force exerted on the electron in electron to the electron by using the electromagnetic lens, the force is directly proportional to the velocity of that particular electron. But in the case of ion beam, these are much heavier, so the velocity of these gallium ions is much lower as they are heavy. So if the velocity is much lower, then they need large magnetic lenses, which is practically not possible, correct? So control of electrons or the focusing of electrons during the electron microscopy in TM or SEM, it can be done by electromagnetic lens very easily. But in the ion beam, electromagnetic lens cannot be used because their velocities are much lower, so they need very large magnetic lenses. However, in ion beam you are using that's why you are using the electrostatic lenses. Why? Because electrostatic lenses use electric field to manipulate these positive ions. Okay, and here the force is independent of velocity of that particular ion, correct? So by using the electric field or electrostatic lens, you can actually precisely control the ion beam, okay, but not in the case of by using the electromagnetic, because the velocity of ions are much slower or lower than the electrons, which are much lighter, so their velocity is very high. So the electromagnetic lens can be effectively used to precisely control the focusing of electrons, but not in the case of ion beam where we use electrostatic lenses, correct? Now after the lenses, you will have also the blanking plates. I talked about these blanking plates, correct? So now during sputtering, when these ions interact with the sample surface, your sample is getting removed. But if you don't want to make the ion beam interact with the sample at a certain instant, then you can use these blanking plates. It can actually, these blanking plates can avoid the unnecessary exposure of the sample during FIB operation. Okay, so they can block the ion beam. That's why they are called the blanking plates. Fine. So this is a general ion optics. Usually we see in the any of the focused ion beam microscopy of the ion column, correct? Now we also talked about the apertures. So you have a source, okay, so your gallium plus ions accelerates towards the column, then there will be a condenser aperture, correct? This is your condenser aperture or condenser lens. Below the lens you will have an aperture, correct, with different sizes. If you magnify this particular aperture below this lens, then what you have is a nothing but a different size holes. Okay, so if you want the larger beam, you are using the beam should pass through this particular large aperture. If you want a smaller beam or the smallest beam, you can change the aperture so that it can change to a smaller beam size. So your beam size will be smaller here, your beam size will be larger here, correct? So based on the aperture, you are actually changing the current, the ion beam current on the sample. So your beam size also will change. In both cases the beam will be focused, but the current ion beam current will be higher for the higher aperture, and the ion beam current will be lower for the lower aperture size. Okay, so this higher aperture, lower aperture can control the current, of the ion beam. That actually directly controls the speed or the velocity or the speed of the sputtering process. Sputtering process. Okay, so the ion beam current can be selected by the beam defining aperture below the condenser lens. Okay, and this is the strip, this is the aperture strip with different sized circular holes called apertures. Okay, and the larger is the aperture, larger will be the ion beam current, and higher will be the fast or higher will be the velocity of the sputtering process. Correct. Now we have discussed about the ion beam and the apertures, even the ion optics. Now we will just briefly go through the some of the physical terms which are very important to measure. Okay, first we will talk about the ion beam current. Ion beam current. So it is nothing but the number of ions that can interact with the sample during a time t. Okay, so you have an ion beam, correct? You have a sample, fine. So this is the ion beam current is nothing but the number of ions that are interacting with the sample during the time t. Okay, so this can be given as n is equals to I cross t divided by c. Here the n is the number of ions, I is the current in amperes, and t is the time in seconds, and c is the charge. Correct. So this is the ion beam current. Another term is the ion dose. Correct. So there are two terms here. One is dose and one is fluence. Okay. So there is a difference between. So what is the fluence? Fluence is the number of ions that pass through an area prior to the interaction with the sample. So if your beam is there, if you have this particular sample, so fluence can be described by this particular area. Just before the interaction, the number of ions that pass through an area, correct? That is called fluence. And dose is the number of ions that have traveled into the sample surface. Okay. So dose is the number of ions that travel into the sample surface, but the fluence is the number of ions that pass through a cross section prior to the interaction with the sample. Okay, so the dose is given by n divided by a. Okay, n is the number of ions, a is the area in centimeter square. Okay, so there is another term which is called ion dose rate, where if you involve the time. Okay, so the dose rate is described as the number of ions that are going through a specific area per unit of time. Okay, so dose rate is given by n divided by a into t. Okay, so time is in seconds. area is in centimeter square, and is the number of ions. So these are the three terms which you usually encounter when using the focused ion beam for the sample preparation. So you need to control the ion dose rate, ion dose, and also the ion beam current depending upon your sample. Correct? So these are the three physical features or three parameters which we usually change during the sputtering process. Now, after describing the section, the briefly the section of the ion column, then what we now go through is the interaction of ion beam with the sample. So, what type of radiations or what type of electrons or ions, what type of emission of waves will takes place when your ion beam interacts with your sample surface. So imagine you have a sample surface, this is your sample, and your ion beam is interacting with the sample. So you have a certain structure of that particular sample on the sample surface, correct? This is your sample surface, and these are the atoms which are arranged inside the sample, fine, which is having a definite structure. Now when an ion beam interacts with the sample, the first emission, the first common emission is the secondary electrons and secondary ions. Okay, so what are secondary electrons? These ions and electrons can be detected by different detectors. Okay, and these two secondary electrons and secondary ions can be used for images to form the image of the sample surface. Okay, the second interaction which is main for the focused ion beam is called the sputtering. What is sputtering here? The sputtering is the sample, so removal of sample surface atoms. Okay, so this sputtering process, when an ion beam interacts with the sample, then the surface atoms can be removed based on the dose rate, based on the ion beam current, correct? So, and this sputtering process is used to cut the structures, cross section, cut the features from the sample. Okay. The third thing is when the ion beam interacts with the sample surface, then it may modify the sample. Means it may modify the sample means it can generate vacancies, it can generate dislocations, and also the interstitials. Okay. Now the interaction of the beam so takes place unless the ion beam travels into the sample surface until all the energy has been consumed. All the energy of the ion beam is consumed. Okay, so it means that it has a certain depth which is called projection range, which depends upon your ion beam current which you are using it, which depends upon the material which is under investigation. Okay, so material for the sputtering process. So the ion beam travels across the cross section of the sample surface up to a depth which is called a projection range, referred to as projection range. Now, so we'll just briefly describe about the secondary electrons, secondary ions, correct? So secondary electron emission, Okay, so this is just the removal of valence electrons from the surface atoms. These are used for the SC image, which is similar to what we use in the SEM, scanning electron microscope. Correct. So there in scanning electron microscope, the electrons will interact with the surface atoms, and there will be a removal of valence electrons. So they will have information related to the surface topography or the surface. Correct. Similarly, by the interaction of ion beam with the sample surface, you can generate these secondary electrons, and it can be used for the imaging. Correct. So here the yield of SE secondary electrons is much higher than the electron microscope. So here if each for an ion beam, for per ion you can actually generate 1 to 10 secondary electrons. But for electron beam or in electron microscope, for each electron you can generate only 0.1 to 1 secondary electron. Okay, so the yield of secondary electrons is much higher in the case of by using the focused ion beam. Okay, next is the secondary ions. Okay, so this is secondary ions are produced due to the high energy collision of the ion beam. Okay, and the sample atoms gets ionized or polarized on the surface. Okay, so and this is followed by these ions can be knocked out. Due to the form of these secondary ions. Correct. And these secondary ions usually they have a chemical information about the specimen surface. Okay, so it is nothing but as in the atom probe, you are depending upon the chemical species. Actually, you will have atoms which are polarized, and they convert to the ions, and they can accelerate towards the detector. Similarly, these secondary ions from the sample surface will have a chemical information. Correct. So these are called secondary ions. Now there is also a backscattered ions. So it might possible that the incident ion, okay, gets travel into the sample surface, and the same ion beam can actually backscattered. Okay, it means that the same primary beam can bounce back. These are called backscattered. Okay, and these backscattered electrons or backscattered ions are nothing but the gallium plus ions. If you are using the gallium ions as the source, correct. And based on the due to the interaction of these gallium ions with the sample, you can also generate heat on the sample surface. These are termed as phonons. Okay, so these can create atomic vibrations due to the interaction, or waves, or we can call as atomic vibrations or waves with the samples which is having a certain crystal structure, and they can represent the form of heat generation into the sample surface. Correct. So these are the basic radiations or basic emissions when your ion beam interacts with the sample surface. Okay, so during the interaction of the gallium with the sample, we also encounter an issue which is called ion implantation. As I told you before, if you have a sample surface, okay, so and if you have a gallium FIB or the gallium ions which are accelerated towards the sample surface, this is your cross section. they can travel into the sample surface unless until the moment where they lose all the energy. Fine. And if they lose the energy inside the sample, these gallium plus ions will remain into the sample. Okay, so this is called ion implantation or into the sample surface. So usually the gallium ions can implant up to a thickness of around 10 to 12 nanometers. So gallium ion penetration depth is around 10 to 12 nanometers. However, in the case of electron, it is mostly in the 1800 nanometers, 18 to 2000 nanometers. So electrons can travel much farther into the sample surface, but the gallium interaction is around 10 to 12 nanometers. And in this surface, usually there will be a gallium implantation because some of the gallium ions loses energy and they can stay into the sample surface. Okay, so the average depth, as I told you, the gallium goes into the sample and it comes to the rest, is called the projection range. It's called the projection range. R project, correct? This is called R projection. So in the case of gallium, when the gallium goes and gets implanted into the sample surface, it can change the physical properties of the sample on that layer, in that layer, physical properties of the sample, which may be crystal structure. You can, if there are presence of grain boundaries, then grain boundary chemistry will change, and some other, you can call it characteristics of specimen. So local composition may change in the solid solution, correct? So this is, we call it as a gallium damage. We usually call it as a gallium damage due to the gallium implantation into the sample surface. Correct. So we'll just briefly describe about the sputtering process. Okay. Then we'll introduce the sputtering process. What is sputtering process? It is nothing but the removal of atoms from the sample surface. Okay. So sputtering occurs when the atoms actually ejects from the sample surface. Okay, so it means that this is a type of displacement where the atoms which are near to the sample surface, they get displaced to the environment. Okay, and the more amount of collision occurs between the ion beam and the sample surface, more likely that the sputtering will occur. More amount of sputtering means more number of atoms can be removed. It depends upon how much the ion beam locally interacts with the surface atoms of the sample surface. Okay, so sometimes it happens that atoms that are located deep into the sample, they are less likely to be sputtered out. Okay, so only the surface atoms are more prone for the sputtering of sputtering process, which is the removal of atoms. So this sputtering process or the rate of sputtering process, it depends upon the surface atoms that needs enough energy for the sputtering to take place. Okay, and also the surface atoms binding energy. Okay, so third is the incident angle, and the fourth thing is the initial ion beam energy. These are the four conditions which usually the speed of sputtering or the sputtering process is controlled by these four factors. Okay, so with this I will end this class now, and in the next class what we'll do is we'll briefly go through this sputtering process, and how it is dependent on the incident angle, and what are the different aspects of FIB which we need to be carefully looked into it. Okay, thank you.